And in this element that now we are seeing on the screen, okay, we obtain the force balance. Now look at the green plane, F, G, D prime, B prime. We have taken the upper portion of that infinitesimal element, look at here. And for equilibrium, we said that we have to apply a force, a shear force, okay? A shear force, as you see here. Vx, right? And this Vx at the end gives us the shear flow VQIZ. I think everything is clear up to this point. Now look, please look at here for a while. This time, I am going to take the lower portion of this infinitesimal slab, lower portion. Previously, we have taken upper. Now, the lower portion of this. I'm going to start from there. Okay. So, the title of today is, okay, the shearing stress equation that you will be using in this course for the remaining portion of the is the following. Let me start. Probably you remember the equation Q, but anyway, I mean, now we will be talking about the shearing stresses in beam, in a beam. Okay. Now, from the beam, which we discussed, mentioned, okay, let's take the lower portion. Okay, now this is the lower portion of that slab, remember. Okay, so maybe it's better to put the letters. This is F, not A, which is a G, G prime, F prime, B, E, E prime, etc. Okay, is this clear? Okay, then say that this distance from here to here is T, and still remember this distance is delta X. And our coordinate system is the following: X, Y, and Z. Let me draw here. There is an upper portion of this beam like that, which we have already discussed. Okay, here we have A, etc. And on this portion, we have this force Vx, right? Now, this was the previous element. Now, I am just putting the shear force on the surface, but now it is in the opposite direction. Okay, why? This is the delta Vx, which we discussed last week, right? So now I am removing this portion. That this is the lower portion of that green plane. Okay, the lower portion of that green plane. We have divided the slab into two, divided horizontal plane. Anlaşıldı değil mi arkadaşlar? Tekrar şuraya çizeyim açık olsun diye. Daha önce şöyle bir slabimiz vardı, hatırlayın. Şöyle bir şey. Now we just divided into two with this. Now we are taking the lower portion. Okay. Anyway, now look. We know the shear force on it, delta Vx. We obtained this last week in detail. Then what is the shear stress? The shear stress tau, okay, xy average, look, tau on the y plane in x direction, which still we call average, is equal to force over area. Okay, delta Vx over delta A. This is the basic definition of the stress. But its direction is in the minus x direction, so there is a minus sign in front. Is this clear? Okay. Now look, We have already obtained delta Vx last week. What is that? That is Vy Qz over Iz. This is the Q value that we obtained, or excuse me, Vx value that we obtained. Now, when we multiply with the delta X from Q, we obtain Vx. Burayı hatırlıyor musunuz arkadaşlar? Bakın bir kez daha geçen haftaya bir geri döneyim. Tekrar hatırlatmak için size. After long derivations, we obtained Vx here, right? Okay, this is Qx. Now, the integral is Qx. So, at the end, this is the Vx value that we obtained. And then, replacing mz with Vy over delta x, the last form of the Vx is this, Vy Qz Iz delta x last week. Now, I am using the same equation, okay, the same equation, and now dividing it to the area. What is the area? It is thickness times delta x. This is the area, right? Now, delta x's cancel each other. So at the end, we get the following equation. The shear stress in the beams, which is somehow average, is equal to, for this problem, minus, or for this cross section, minus Vy Qz Iz times T. So this is the equation that you should know well for the beams. This is the shear equation for the beams. Actually, we, in speaking, call it as follows. V Q over IT, without referring to it as subscripts. V Q over IT. This equation is the equation that should be used in the beams. So please do not use this equation, which we have used for rivets, pins, bolts. In the beams, this is the equation that you should be using in the examinations and in your designs. Okay. So this is the shear equation. And don't forget that Iz is the total moment of inertia. Okay. Buraya kadar bir soru var mı? I expect you to know this equation very well. And let me write once more. Here, Iz is the centroidal, okay, centroidal moment of inertia of the entire section. Don't forget, of the entire section. Why I am writing this? Because I said that this part, this figure is a half of the slab. Maybe half, maybe a part, let us say, of the slab, not the entire cross section. But the I should be the moment of inertia of the entire cross section. So shortly, the shearing stress in the beams is obtained with this equation, V Q over Iz. Now, consider the previous beam. Buraya kadar sorunuz var mı arkadaşlar? Consider the previous beam again. Consider the previous beam again, the beam which we have started with. Now, on this beam, remember, we had such a cross section. This is not a slab, the whole beam. It goes like that, okay? And on this beam, we have, say, centroid somewhere here. And we have already attached a coordinate system, which is X, Y, and Z. And further, on the cross section, we have a shear force. Look, on this cross section, say that we have this shear force. Look, this one, Vy. Keep in mind that whenever we have the shear force, there always exists a moment coupled with that. Although in our book, this moment is not shown in the problems, keep in mind that this shear force is always coupled with a moment. Don't forget this. Tekrar ediyorum. This shear force is always coupled with the moment. Okay. Now, let us take two elements here. One at the top, somewhere here. Okay. Onur, Yeni mi katıldın, ekranın mı kapandı? Now look.
Yok hocam, bayağıdır buradayım.
Peki. Look, we have a cubical element here and another element somewhere here. One at the bottom, one at the top. Now let's take this element and draw the stress on it. You should draw these stresses by now very easily. Okay. Now look, this is the cubical element at the top. Because I'm drawing it because it has an importance as long as the stress distribution is considered. And now let's take the lower element here. So we have a similar cubical element at the bottom. Okay. Now, when you consider these cubical elements, obviously, just a minute, please. Let me draw a better cubical element here. This one. Now look. First of all, what you expect is this. Because of this shear force, you are expecting a shear stress here, which is tau on the x-plane in y direction, having the same direction with Vy. Burayı takip edin. And also, we have another shear, we are expecting another shear stress here, which is tau. It is normal, the normal of the surface is x, direction of the shear stress is y, and it's minus. Okay, so since we have the shearing stress, we are expecting this one at the top, this one at the back, and excuse me, it should be in the opposite direction. And also this one at the bottom, right, in general. Again, I am expecting the shearing stress like that here, another at the bottom, and here at the back. We know this. We know that the shearing stress at the top is tau yx, and this shearing stress at the bottom is tau yx again. Is this clear? This is what we are expecting in general. However, I said many times before. Now look at here, please. Is there a load on the surface? Any load, any external force? Yes? In this problem, is there a given external force there?
No.
No. So therefore, this must be zero. In the same manner, there is no external force at the bottom, right? So, the shearing stress here is also zero. Now, since these are zero, then this must be zero and this must be zero. Is this clear? Therefore, whatever the shearing stress distribution is, at the top and at the bottom, the shearing stress is zero. Okay, at the top and at the bottom, the shearing stress is zero. Buraya kadar bir soru var mı? Okay. Anlaşıldı değil mi arkadaşlar? Bunu birçok kez söyledim. Eğer yüzeyde bir kuvvet yoksa orada stres de yoktur. Now, okay, now let me write this result. Since no force exerted, on the upper and lower surfaces, on the upper and lower surface, as you see, okay, we have tau yx is equal to 0. It follows that, okay, it follows that tau xy is 0. Okay. Now look, why we have written average to this equation, average? It is because of this. Now let's take that slab once more, okay, which we have started with. Now on this slab, we have a shear force Vx, and we obtain the shear stress Vq over IT. Okay. Now look, the shear stress has such a distribution on the cross section. The shear stress, which we found by VQIT, now let me just draw a figure indicating that, has such a distribution on the cross section. Now this is the shear stress at the ends, okay, like that. However, it is lower in magnitude in the middle portion, like that, okay. Clear? So what we are calculating is an average value, something like this. This is tau xy average. Why? Because remember the notation that we use, we have fg, f prime, g prime here, and b, e prime, etc. Now, if you say that this point is g double prime here, this point is g double prime, what we know is that tau, okay, tau xy, which we calculate with this equation, at g and g prime is greater than tau xy at g double prime. Is this clear? So in the middle portion, there is a decreased shear stress distribution, which you can determine by elasticity. Burası tamam mı arkadaşlar? That's why we are saying it is average. But of course, it is much more accurate than the equation we use for pins, which is F over A. Oldu mu? Now, I can also say that for a rectangular beam, for a beam of rectangular, generally we have such beams, rectangular cross section, theory of elasticity shows that okay, if B is smaller than h over 4, this variation, tau max, is equal or smaller than 1.008 tau average. Okay, so where is tau max? Look, this stress here is tau xy max, and this stress here, let me rewrite it, is the average value. So what we are calculating is an average value. However, if your beam's cross section, just take such a beam. Generally, beams are have greater dimensions along their heights because of the moment of inertia value that you are expecting to keep it high. So if you say that this is h, and if this is b, say, so if b is less than h over 4, this variation can be regarded as insignificant. Okay, clear? So say b is the width of the beam having a shear stress, of course, on it. Buraya kadar bir soru var mı? Shortly, the shear stress in the beams is obtained with this equation. Tau is equal to V Q over IT. This is the stress equation, just like MC over I, T, C over J, F over A. This is our fourth stress equation. Axial loading, F over A. Pure bending, MC over I. Torsion, T, rho or R over J. And shear, V, Q over IT. Now we learned all the stress equations that we need for elementary theory. Okay. Now, of course, I didn't write any subscript here because it depends on the coordinate system that you have selected. I'm going to make these further clear. Maybe we can start with shearing stresses in common types of beams. So, shearing stresses, follow this carefully, please, in common types of in common beam types. Okay, let me just use this, exactly the same title, in common beam types. Now, maybe an example of this, general I-beams are used, but we may start with a rectangular beam. So look, for the following for the following. For the following narrow rectangular beam under shear force. So what we are saying is this: we have such a beam, a rectangular beam, okay? And this beam has such a coordinate system, say X, Y, and Z, right? Of course, these are centroidal, not any three axes like that. Maybe I should correct also this to make the figure more understandable. Anyway, this is the centroid, etc. Now look, if we have a shear force here, say that the shear force is this is the centroid in the vertical direction. Say that this is V, Y. Of course, this should be coupled with a moment, always, whether it is shown or not, MZ. This is our case, right? For this case, again, as you always do, we have to look at the cross section. So, at any point Q, what is the meaning of that? I am looking for the shear stress at point Q. So, first, I should refer to a cross section which that point exists. So say that this is the cross section of the narrow rectangular beam. Say that this is the, okay, let me redraw it. Let me extend that a little to clearly identify the figure, okay? Say that this is a narrow beam, right? And these are the axes that we are using. Say this is Y, this is Z. Here is the centroid. I am saying that at this cross section, we have a shear force Vy, and we have a moment Mz. It should be coupled with that. Now, if I am looking the shear stress at point Q here. Arkadaşlar buraya dikkatli bakın. I know that this is also the neutral axis of the cross section. I am looking for the Q. Now, if possible, because I'm going to change this later, if possible, draw a line parallel to neutral axis and passing through Q and dividing the shape into two. Dinliyorsunuz değil mi? Draw a line parallel to neutral axis if possible. Because another thing may be asked, but for now, let us say this is the case. And passing through Q and dividing the cross section into two. So now you have two areas. One is this. One area is this. And the other one is the remaining. It is not important which one you are using. Use the simplest one. Okay. Now, what was our equation? Our equation was this. How on the x-plane in y direction is equal to minus Vy Qz Iz times t. This is the equation. Now, what is Qz? Qz is the first moment of this cross-hatch area. Is this clear? Remember the derivation. So, simply just determine the centroid of that area. This is the centroid, right? Then, if this is the, let me draw it here. If this is the location of the centroid from the neutral axis, okay, if this is the location of the centroid from the neutral axis, we all know that Q is equal to following. Look, Q, Z is the first moment of that area about neutral axis. What is the area? It is A. What is the centroid? Y bar. Now this is Q. Shortly, it is equal to, look, okay, what is area? Let me put a few data also. Say that this Q is Y away from the neutral axis. say that this is C, which is equal to 1 over 2H, right? This is also C, which is equal to 1 over 2H. And let us say that this is B. Now, in this sense, what is the area? Simply, area is B times C minus Y. This is the area, right? What is Y bar? Simply 1 over 2 C plus Y. I mean, you can easily verify these. As a result, Q for this area is equal to 1 over 2 B C square minus Y square. Oldu mu arkadaşlar? So, let me repeat. If you are looking for the stress at point Q, first divide the cross section into two. I'm talking about a practical way, of course. And then this line, which divides the cross section into two, should pass through Q and must be parallel to neutral axis. Then you are taking the moment of inertia QZ. Look, I'm going to say one more thing, although I'm going to raise later. If you calculate the Q of this area, buraya bakın lütfen. If you calculate the Q of the remaining area, you end up with the same magnitude, but opposite sign. Because when you add, they must all be 0. Okay? So you can use both. This is the centroid of that area. Buraya kadar bir sorunuz var mı? Çünkü bundan sonrası çok straightforward. What about IZ? You all know that IZ is the total moment of inertia. 1 over 2b h cube is our classical equation. For this problem, 1 over 2, b is again b, h is 2c cube. So it is equal to, for this problem, 2 over 3 b c cube. Then what is tau xy at point Q? Okay. Now we determined everything. Then tau xy at point Q is equal to, okay, again, let me write at Q, is equal to sonucu yazayım isterseniz bunların hepsini yerine koyarak. Ya da şöyle yazalım, biraz daha tek tek şeyleri yazalım. Okay, Vy is Vy. Look, in this equation, T, bakın arkadaşlar gene pratik bir şey söyleyeceğim size. T is the length of this line dividing the body into two. So T is B. Okay. Then, of course, you can calculate easily tau xy. It is equal to minus 3 over 4 c square minus y square over b c cube vy. So, for different y values, you can determine tau xy. Be careful, when c is equal to y, the shear stress is 0. Or you can further refine this equation, since A is equal to 2BC, right? You can again write this equation, tau xy, as minus 3 over 2 V over A, Vy over A, 1 minus y square over c square. This is how you use this equation. Anything which is not clear, which is not understood, which is not clear for you. Oldu mu arkadaşlar? Nasıl kullanılacağı? Peki. Soru yok, anladığınızı varsayıyorum. Doğru mu? Okay. For this cross section, let's look at the distribution of the shear stress. Hence, distribution of shearing stress, distribution of shearing stress is, now look, this is the beam that we were talking about. Okay. And this is the y-axis. And this axis is the tau xy average axis. If you look at the above figure, this stress distribution in a, let me complete the sentence now, in a transverse section of a rectangular beam, section of a rectangular beam, which is this one, right? Okay, is the following. Now look at the above equation. When y is equal to C, stress is 0. When y is 0, it's maximum. So we can say that this distribution, it is very clear from the figure, is parabolic. Okay, is parabolic. So what you have is the following. Let me change the color. Okay. You have such a stress distribution where you have tau x, y, or yx max here. So shear stress is 0 at the top. It increases towards the middle portion and decreases again. Any question? Takip ediyorsunuz değil mi arkadaşlar? Peki. Now, what about the I-beam? For the I-beam, although we have to use VQY directly, but there can be a simple approximation for the solution, because I-beams are frequently used in the structures which are used to construct beams. So for an I-beam, using tau xy equals to minus Vy Qz Iz T. Now look, I am using subscripts and sign being different from the book to make you to understand the use of these equations well. Okay. Now look, if we have such an I-beam, this is an I-beam. We know that, probably you remember, why do we use I-beams? Because whenever there is a shear force, there is a moment, there are normal stresses due to the bending, and we want to keep I value of the cross section as maximum as possible, and I-beam is very appropriate for that, right? Anyway, this is the z-axis, this is the y-axis. If you draw the shear stress distribution for this cross section, what you obtain is something like this. Again, this is the y-axis, and say that this time this is the tau xy average. In the same manner, look, the stress first increases. It is 0 at the top and 0 at the bottom. We know it. Don't forget, the shear stress, which you obtain from VQ over IT, is always 0 at the farthest point from the neutral axis. 0 at the farthest point from the neutral axis. So it increases, okay, like that, and like that, towards the middle portion. But suddenly, when you reach this web point here, look, in the equation, this T changes. Q is almost the same, but suddenly T decreases. So, although not so sudden, the stress changes. Is this clear? Because of the T. And again, it gives such an area where here, okay, let me correct the figure a little. Okay, so somewhere here, we reach the maximum value where it is tau max. Okay, this is tau xy max. Bu step anlaşıldı değil mi? T1'den değiştiği için. T suddenly changed. So this is tau xy max. We have such a stress distribution. Because of this, in practice, sometimes don't use this in the examinations, but in practice, we can also say that the stress distribution tau max is approximately V over area of the web, ignoring the stress distribution at the top and bottom. But more important for us is the stress distribution that sudden change because of that T value. Buraya bir daha bakın arkadaşlar. Her ne kadar sileceksem de. Now look. What is T? T is the line, is the length of the line dividing, daha küçük çizim esasında. T is the length of the line dividing the body into two. Like that. But here, T is very small. Is this clear? Okay. Arkadaşlar, bir kadar anlaşılmayan T var mı? Şimdi stres elementleri teorideki bütün denklemleri çıkardık. Stres denklemlerini bitirdik. Bir de problem çözelim. Problemi çözmeden bir kez daha hatırlatayım. We learned two equations at the end. One of them is the stress equation. We Q over IT without referring any coordinate system in basic. The other one is the shear flow. This is the stress equation. This is the shear flow, which is V Q over I. Now, what's the difference? The only difference is thickness. One is the shear flow per unit length. The other one is the stress by dividing it to the width. So this is, for example, newtons per meter or millimeter. This is, this one is newtons millimeter square, megapascals. So we are dividing, okay, remember, we divide Vx to delta x, obtain Q. We divide Vx to delta x times T, obtain tau. Okay, shear flow is the total shear force defined per unit length. Shear stress is the stress that you very well know by now. Okay, we have two equations. They are almost the same. In the Q, we don't have T. In the tau, we have T. Now, in this respect, remember, I said that we use this equation, this Q equation, whenever there is nail, rivet, pin, not a continuous connection between two parts of the beam. Okay. Now, an example is the following. Bu iki equation'ı bence aklınızda tutun. Sınavda biz bu dönem veriyoruz. Ben genelde vermem ama bu dönem veriyoruz. O yüzden ezberlemenizi isterim. Çünkü bunlar çok artık basit 4 tane denklem. Yani bunu by heart bilmeniz lazım. Her neyse. Şimdi gelelim probleme. Birkaç problem çözeceğim. Çözebildiğim kadar bugün. Okay. Gene kitaptan kopyalayacağım. This is chapter, what? 6, okay. Chapter 5 is just a repetition of the chapter statics, excuse me. So there's no need to go through that. But if you think that you forget it to some extent, please go through that. Okay. Now, this is the statement of the problem. This problem is simple, but it is very useful to understand the use of not shear stress, but Q. Copy and paste. Burayı iyi takip edin lütfen. Okay. Look. There are 3 boards, wooden boards. Their cross section is 50 by 100, and say that they are very, very long. Forget about their length for a while. And they are nailed together. So as you see, with equal distances, 2 nails are used for upper and 2 nails are used for the lower planks to join them and form a beam. And there is a vertical shear. I don't like this notation that book is using. I always use a coordinate system and the direction for the shear. It is meaningless to write like that. But anyway, we don't know whether it's upwards or downwards, although it doesn't change the problem solution. But anyway, so we know that there's a shear force, pardon me, we know that there's a shear force of 1,500 newtons, and further, what we know that each nail can resist a shear force of 400 newtons. So if a high shear force applied, it fails. So we are looking for the largest spacing between the nails. Is this clear? Okay. Now, if we are going to solve this problem, you should do this. First, refer to the cross section, as we always do. Now, say that this is the cross section of the beam. Okay. Now, there are three boards, upper one, middle one, and lower one. I'm going to attach a coordinate system. In mechanics, without a coordinate system, you can't solve anything. Y, say, and Z. And the shear force is given. Direction is not given, but I am assuming that the direction of the shear force is in the downwards direction. And we all know that whenever there is such a shear force, there must be a coupled moment. Although it is not our concern right now, we know that there is a moment. Otherwise, we don't have the shear force. Now, this is the situation. Then, again, we know it is centroid. Now, look. Since the shear force at the nails are considered, the important surface for us is the surfaces where these boards are in contact with each other. There are two such surfaces. Because of symmetry, let's take only one of them, the upper one. Now, here, I am selecting an area, just I did previously, okay? I am going to use this area to calculate the shear flow, not the shear stress. Now, this is the centroid of this area. And I know that this is also the neutral axis of the cross-section, because in this course, we are only using the symmetric cross-sections. And then I know that this distance is y bar, which is equal to 50 millimeters, right? Now, I am looking for the value of Q. I am looking the shear flow, Q, which is Vy. Remember the equation, Qz, Iz. Now, looking for shear flow. Now, let's first calculate it. Now, first of all, moment of inertia is very clear. Iz is equal to 1/12 BHQ. Don't forget, B is, in this problem, 1/12, first of all. B is the width, 1,000 millimeters. Important thing is that this is the moment of inertia of the whole cross section. So multiply 50 millimeters by 3, not a portion of it, always. And that's equal to 28,125,000, okay? And now I am looking for QZ. What is QZ? It is the first moment of the related area. The related area in this problem is the cross-section of the upper board. Okay, so it is nothing but AY bar. What is A? A is the cross-section of the upper board. It is 50 millimeters times 100 millimeters, the cross-hatch area. If I multiply this Y with Y, if area, this with Y bar, which is 50 millimeters, then what I get is the first moment of area that comes as 250,000. Okay. So from here, I can calculate the shear flow Q. The shear flow Q is Vy, which is the shear force applied. I am using the magnitude of Q, although it's positive here, 250,000. Okay. And now I am dividing it to the moment of inertia, which is 28,125,000. Okay. So what I get is the value of the Q. Remember, it is shear force per unit length. It is 13.33 newtons millimeter. Şimdi bunu ne yaptık? Şunun için yaptık. Şu şekli bir çizeyim. Tekrar silelim. Şimdi arkadaşlar alttaki iki plank'i düşünün. Board'u düşünün. Just think about these two boards at the bottom. On these two boards, we have a shear flow Q. Okay. Now, middle one, lower one. On between the upper one and this, we have shear flow. I'm going to raise. Per unit length. This is Q, right? On the cross section. We calculate this. So this Q is the shear force acting per unit length between upper board and middle board. Buraya kadar bir sorunuz var mı? Nereden geldi? Derivasyondaki delta Vx'ten geldi. Shear force'dan geldi. Hatırlayın. Oldu mu arkadaşlar? Şimdi soru şu. Neyleri nasıl yerleştirelim? Bakın. This Q is per unit length. So, turning back to here, you can say that, şuraya bakın arkadaşlar, yani bunu şöyle düşünün. Neyse, bu kafanızı karıştırmasın, tekrar şurada çizeyim. Şimdi bunu tekrar siliyorum. Çünkü orada çizersem üst düzeyde olacak. Biraz daha büyüterek çizeceğim tekrar. Bakın. We have middle board here and lower board here. And they are going like that. Okay. Forget about their length. Say that they are infinite for our case. Now, we have nails. One nail, two nail. They are going like that. And I have shear flow on this board like that. Okay. On the whole surface. I can think that these two nails, for example, can carry the shear force which is defined on this area. Is this clear? So these two nails say that is responsible for the shear force there. Maybe these two is here. Okay. So as a result, I can say that this Q, when multiplied with this distance S, now it was Q before, it is newtons per millimeter. When multiplied with S, millimeter, then the force that I find here is carried by these two nails. Oldu mu arkadaşlar? Arada per unit length bir shear flow var. Bunu S ile çarparsam bu shear force'u, artık shear force'u bu iki tane çivinin taşıdığını varsayabilirim. Okay. I can assume that these two nails carry the shear force Vx, let us say. X miydi bu yüzey? Önce bir koordinat sistemine bakayım. Evet. Which is obtained by Q times S. This Vx is carried by two nails. And this with this with this, etc. So as a result, I can say that, okay, şunları da sileyim. Q'lar devam ediyor sürekli. Okay. On the whole surface, we have these Q's like that. And here are the nails. Aklınıza takılan bir şey varsa lütfen sorun. Anyway, now, at the end, I can say that, let me complete this problem for the break. I can say that this shear flow, Q, between these two planks, which is newtons per length, when multiplied with the distance between the nails, gives us a force, and this force should be carried by the nail, but in each distance S, I have two nails, so this is our equation. Therefore, S is equal to F2F nail over Q. Or we can say that S is equal to 2 times, we know that each nail can carry a force of 400 newtons, And we have already calculated Q as 13.33 newtons millimeter. So S comes out as 60 millimeters. Therefore, if you use a larger space between these nails greater than 60 millimeters, these nails will fail. Okay. Any question? Let's stop here and continue that in the second hour. Burası anlaşıldı mı arkadaşlar? Anlaşılmayan bir şey varsa lütfen sorun.